Okay. So this will be graphs of basic functions. This is section 2.6. The first thing we're going to do is we're actually going to define a concept that is really uber important, especially in calculus. Although, just because it's important in calculus, it's still important to the whole of mathematics. We're going to define what it means to be continuous, but we're not going to give a truly good definition of it. We're going to kind of give a basic one because the real definition of it does involve certain calculus concepts. A function is continuous, and I'll underline that word in a second, over an interval of its domain. So just whatever you're talking about on its domain, oh, it's continuous between these two numbers here. If its hand-drawn graph can be sketched without lifting your pen or pencil. That seems a little bit weird at the get-go. We will put a nice box around this word continuous. I mean, it kind of is what it sounds like. If something's continuous, it means it's nonstop, can't stop, won't stop, you know. It can keep going and going and going. And there's no point where you interrupt the process. So a good example, and let's look at the graph. A good example of something that would be continuous, there's many. Imagine a line. Imagine you were just drawing a linear function. Maybe it has this y-intercept. It clearly has a positive slope. We'll put the arrowheads there. Remember, the arrowheads technically aren't part of the graph. So I did technically lift my pencil to draw them, but it's because they're just visual indicators of something. They're not actually on the graph. But looking at the line, if I wanted to draw this line, would I ever have to lift my pencil, my drawing tool, whatever? It doesn't look like it. It looks like I'm able to just keep going. In the words of the prophet Limp Bizkit, we keep rolling. So this would be continuous. You can keep drawing it without interruption, basically. You can think of it like that. So again, if you're planning to take calculus, you are going to revisit this concept of being continuous, of continuity, except you're going to throw in, you're going to talk about limits, and you're going to say something's continuous only if its limits from the left and right agree and exist, and the function evaluated at every point is equal to what the limits are. So it actually gets a lot more detailed. This is just kind of a quick and dirty definition of it. Let's look at another graph. And oh, let's draw a purple function. Let's draw a purple function. Let's say I was doing something that almost just looks like the parent cubic function. Well, again, I was able to draw this one without interruption. Again, the arrowheads aren't technically part of the graph, so it's okay. I lifted my pencil to draw them. This is once again a continuous function here. If you can just keep going, no interruption. But where it might, something that might fail to be continuous, well, imagine I started drawing it, and then I decided that, all right there, Pilgrim, I want this thing to now look like a line. Something like that. Well, you're probably thinking, wait, Josh, you just completely changed the shape on us. And yeah, that's something that's possible. You can define what is called a piecewise function, and we'll discuss those today. And with a piecewise function, you can totally just drop the graph, change it up like that. So notice that right here, I had to lift my pencil, I had to change things. What we might say is there might be a hole there, and then the graph at this specific x value continues on starting with that point. But this is not continuous. This is said to be discontinuous. You had to lift your writing utensil to draw the graph. At some point, you interrupted your process. It wasn't just a nice, smooth process. So that's a basic idea of continuous. Again, it's very basic. That's really, I would almost argue that's not a good definition at all for it. It's just a way for you to catch it visually and see what's going on. So that's just kind of like a little bonus thing we discuss here at the beginning of this section. But we will possibly revisit the idea of being continuous, especially when we are talking about graphs. But now let's talk about parent functions. Parent functions. These are going to be the graphs of some of the basic functions, and they're all going to have different shapes. And so this is actually, maybe I won't overthink it. Let's not overthink it. Let's just jump right in. Let's say you're talking about a parent function, f of x equals just x. Now, what a parent function means is we're just saying what are the different categories based on the shape they're going to make. So when you see just x, you're automatically telling yourself, well, there's a 1 in front of there, and then you could pretend like there's a plus 0. And the only reason I bring that up is that means that just the function x is a line with a slope of 1 and a y-intercept of 0, 0. So that's interesting. Now we know lines can take all kinds of different shapes. You can change the y-intercept, you can change the slope of the line. But the idea behind a parent function is simply this is the basic general category of things that are going to have the same shape. And so we already know what a linear function will look like. Specifically, this line looks something like that. Bada bing, bada boom. And so, of course, there's all kinds of things. You can move it up and down. You can change the slope of the line. It does cross through the origin there. And yeah, so this is the basic shape of a linear function, but we already knew that. This next one you might have also already known, the parent function for a quadratic. The most basic representation of a quadratic is just x squared. X squared. Now we already know that quadratics take the shape of parabolas. Now there's all kinds of things, again, I can do to this one. I can move it around, shift it, but the parent function just investigates the basic shape that's going on. In the next section, we'll discuss what we can do to that basic shape and how it affects the formula for the equation. But now, this just creates a standard parabola, and in fact, it's a parabola that touches at the origin. It's symmetric, short of my drawing. Let's try again. Well, it's symmetric in a sense, in the loose sense of the word. Basic parabola, it's like a bowl shape. What you can do with that, you can shift it up and down and all around. You can reflect it over the x-axis so that it'll look like it's frowning instead of smiling. Something like that. You can squeeze it as well. You can do a horizontal compression. So there's all kinds of things you can do that parent function, but this is the basic shape that it would take. So not super interesting, a parabola. What about the cubic function? Where you're just cubing your variable. Well, I'll show you the graph, but I don't like just showing it to you and saying, memorize this. We want to actually deconstruct what's going on here. We want to make a deconstruction of this, not unlike how Star Wars The Last Jedi was a deconstruction of Star Wars, and it was also completely unnecessary, and also that movie sucks. And I walked out of that saying, my faith in the world is gone because of a movie, because that's how much of a nerd I am. So the cubic function, it's kind of hard to draw. It is continuous, so technically I can draw it in one fell swoop, something like that. It's got some curvature to it. Um, it points downwards over here, upwards over here. Um, Explaining the why behind the graph, why does it work, WHY? Uh, you look along the x-axis. When you're going on the positive side of the x-axis, think about it. You're putting positive x values into the function, and when you cube a positive number, it spits out positive numbers as well. So the graph's going to be on the positive y-axis as well whenever x is positive, and it does cross to the origin. However, when you go to negative x values over here, you plug a negative into the cubic function, it actually keeps it negative because it's an odd power. So you do like -2 cubed, it'd be -2 times -2, which becomes +4, but then you multiply it by -2 again to get -8. So this graph is actually behaving as it should. You plug negative x values in, you get negative y values out of it. Again, compare that to the quadratic function that we just did real quick. Compare that to the basic parabola shape. And what we see is with the parabola, that's not quite the same thing at all that's happening. With the parabola, as you put positive x values in, you're squaring them so they stay positive, so the y values are also positive. But when you put negative x values in, you're squaring them, and negative numbers raised to even powers, they go positive. So suddenly this graph of a parabola makes sense. Put in a negative x value, you should get a positive y value, which is the opposite of what's happening with the cubic function because you have an odd power on that. That's actually going to be really telling for what we're doing here. In fact, a lot of the most interesting things in all of algebra simply have to do with the highest power you see. Is it a true polynomial? We'll define a polynomial later. But also, is that highest power even or is it odd? And that can totally change the interpretation of what you're doing, like drastically. Now, you could keep going down the line. You could say, oh, well, what is there? Is there an x to the fourth parent function? Is there an x to the fifth, x to the sixth? Sure, but once you have a basic idea of what positive and negative numbers do when you plug them into those functions, we don't need to focus too heavily on those. So there is a fourth degree function called the quartic. There's a fifth degree function called the quintic. But if you understand why the x squared and x to the third power, why their graphs look the way they do, you can kind of extrapolate that for any power. In other words, we're not going to go into uber detail about them. Next up, f of x equals, how about the square root of x? Now you're playing with power, Nintendo power. You're talking about the square root. Talking about the square root. Let's think about what the square root does. Remember the domain of the square root, the valid x values. You can't plug negative numbers into the square root and expect to get real numbers out of it, which means when you graph it, you have to completely ignore negative x values. So when we graph it, this side of the x-axis over here is going to get no love. It's going to get no love. It's going to be all on its own in this world. So there's not going to be anything on the graph over here. So that actually makes logical sense. The smallest x value that will finally have some magic happening is when x is equal to 0, because you can plug a 0 into a square root. You just can't plug a negative number in. And when x is 0, you take the square root of 0, you get a 0 for y as well. So what that does is that means that the origin is a point on the graph. Now going forward, going forward, you'll have on the positive x-axis, you can do that. You can plug positive numbers in. They may not come out pretty. You may not get pretty y values out of it, but that's usually going to be the case. And now when we did x squared, the thing shot up really quickly. But for the square root of x, we see that taking the square root of something basically makes it smaller, as long as you're taking the square root of something greater than 1. So it's not going to pop up so quick. It's going to kind of take a slow ride there. There is curvature to it, though. It's not a line. It is definitely not linear. There's some nice curvature to it. It does bend. And so bada bing, bada boom. So this is a basic graph of the parent function for the square root. And a few key points on there. If you plug a 1 in, you're going to get a 1 out of it. You plug a 1 in, you take the square root of 1, you get 1. So that means the point 1 comma 1 is a point on the graph. Now, if you plug a 2 in, you're going to be then taking the square root of 2, which is ugly. It's ugly. It's like 1.4 and then some change, and it's nasty. So instead of using 2 as the next point, let's use a perfect square. Let's use 4. Just because it's going to make some convenience for us. So if you plug a 4 into the square root function, it's going to spit out a 2 for y. Thus, the point on the basic parent function of square root x, the point 4 comma 2. If you were doing f of x equals x squared, the point 2 comma 4 is on that. In fact, if you look at f of x equals x squared, the x and y values for each and every point on it are just flipped. They're just flipped versions of this. And then there's also a whole extra part of the graph on f of x equals x squared. So that's actually kind of interesting, because that brings up the concept of inverse functions, of functions that kind of undo each other, so to speak. So we'll keep that in the back of our minds. But this is the square root function. Now, my family hails from the Midwest. Now, I was born and raised in the great state of Texas. I've lived my entire life in the great state of Texas. But my parents grew up in the Midwest. One of them hopped around from Nebraska, Iowa, Illinois. The other one was in Iowa, Nebraska. And so, I'll hear my dad, he's talking about washing something, and he'll say, "Wash. I need to go wash that." And I'll say, "Father, that is wrong. You cannot pronounce it that way. The way I pronounce things is always right." That's not true. But anyways, so I'll hear that. So sometimes you might hear me bust out my Midwest dialect, my Midwest pronunciation of things. And instead of saying square root, you might hear me say square root. It's the square root, which is a very Midwest thing. So you might hear me root, you might hear me root. And you know what, folks? That's about the most interesting piece of information you could ever ask about me. You say, "Josh, what's something interesting about yourself? Have you traveled the world a lot? Have you, done all these kinds of cool, amazing, wonderful things that you can tell us about?" And I say, "Well, sometimes I pronounce square root as square root." So yeah, that's kind of my life story there. All right, all right. It's always hard to tell if you guys are laughing, smiling, Um, so that's okay though. I just always assume nobody finds me funny, and I play up to that. All right, so let's talk about the cubed root. The cubed root. So we weren't allowed to take the square root or square root of a negative number. Negative numbers, we said, we can't do that. You can't take the square root. Now, you remember in chapter 1, you can take the square root of a negative, but you got to involve I. And when we're talking about graphing, we don't want to bring complex numbers into it. Graphs, the x and y axes, are both just real number lines, so only real values. The cubed root, though, you can totally take the cubed root of a negative number. You can't take the square root. The square root is really just the second root, or the fourth root, or the sixth root, and so on and so forth. You can't take an even root of a negative number and expect a real number out of that. You just can't. You can't do it. It's not going to happen. But that's kind of like a little aside over here. The cubed root, you can take the cube or third root, the fifth root, the seventh root, etc. Whatever odd number you want, you can take that root of a negative number and get a real value out of it. You can also do it to a positive number. You can take the third root, fifth root, seventh root of a positive number and still get a real number out of it. Don't believe me? Well, imagine what, let's see. Let me use red here. Imagine the square root of negative 64. Taking the square root of a negative 64. We know it's a square root because if there's nothing written on the perch here, it's automatically implied to be a square root. Well, you can do it, but it's going to involve I. Remember, you take an I out. Don't put an I out. You take an I out, and then you can take the square root of 64 and get 8. But the whole problem with that is that's a complex number. So put another way, when you're talking about graphing, you can't take the square root of negative numbers for graphs. But let's think about what the cubed root of negative 64 would be. Cubed root of negative 64. So if you're taking the square root, you're looking for a number that multiplies to itself and gives you whatever you're taking the square root of. For the cubed root, you're thinking, what's a number that multiplies to itself a total of 3 times and gives you negative 64? Well, if I was just taking the cube root of positive 64, it would be 4. Because think about it. If you do 4 times 4 times 4, 4 times 4 is 16. 16 times 4 again is 64. And it also turns out that it's okay if I just instead do negative 4 instead of positive 4. These two will become positive 16, but there's an odd man out. In fact, that's a good way to think about it. Odd powers, odd roots will retain the negative because there's always going to be one negative number that's left out. And so I get negative 64. So put another way, the cubed root of negative 64 is negative 4. Ooh, so that means I can take odd roots of numbers, of negative numbers, and I still get a real number out of it. It's a negative real number. There's no I involved with this, so it's totally fine. So now let's think about that in terms of the graph. Let's think about graphing wise what the implications are for that. When we did the square root, the whole negative x-axis got no love. But when we take cubed roots, fifth roots, seventh roots, the negative x-axis will get some love. So let's do a bright green. So it's a little hard to draw. So on the positive x-axis, yeah, you get positive y values. On the negative x-axis, though, you still get something. And there's some symmetry there. It's kind of hard to draw. But imagine it was like this, and then it was symmetric about, almost like a sneaky snake or something. So you know what? Let me actually just try to draw that better. Well, no, I failed at that. But the idea is that um, it's going to be there's going to be some interesting symmetry going on here. Maybe something like that. It does have curvature, and it makes sense. You put positive x values in, you get positive y values out. You put negative x values in, you get negative y values out. And again, there's all kinds of things we can do to this. We can reflect it about the x-axis. We can reflect it about the y-axis. In fact, we learned there's something interesting. If you reflect this about the x-axis, and then you reflect it about the y-axis separately, those two come out the same. But we'll investigate that later on, what that kind of symmetry means. So we know now how the x squared, x cubed, square root of x, cube root of x, we know what their parent functions look like. And we're not just taking it on faith. You don't just memorize shapes and say, this is the shape for it. I want you to understand why those shapes make sense, where they didn't just come out of nowhere. So now let's look at another one. This one's going to be funky. We're going to talk about the absolute value. Absolute. The absolute value function. And you guys might recall that what the absolute value does, if you take the absolute value of a number, it measures its distance from zero. That's all it does. And it doesn't care which direction, whether it's a negative number it started out as or a positive number. So when I plug positive numbers into the absolute value, it leaves the number alone. If I put 7, if I took the absolute value of 7, the answer is just 7. If I put 0 into the absolute value, I just get 0. But if I put negative numbers into the absolute value is going to slap away the negative sign. So the absolute value of negative 3, maybe I'll just write it down. The absolute value of positive numbers stay the same. The absolute value of 0, it looks like a TIE fighter, 0. But then if you take the absolute value of a negative number, it just slaps off the negative sign. It says no. And that's because negative 3, even though it's to the left of 0, it's on the negative side, negative 3 is just 3 units away from 0 along a number line. And absolute value doesn't care which direction. Okay, that's interesting. Now, if I go back and I play Everybody Wants to Rule the World by Tears for Fears, and we go back a little bit in time and think of the halcyon days of our youth, if we remember this one, that created a line that looked something like this. I'm going to draw it in 2 parts, and you'll see why in a moment. It went something like that. It had the arrowheads on either end. I'm actually going to omit the arrowheads for the moment, but just it's a line that kept going and going, going and going in this direction. That's when we just had x by itself. This thing is very similar to that, except it adds on the restriction that if you plug a negative x value in, it needs to make it the positive version of that. So Along the positive x-axis here, anything that was positive stays positive. So actually, this part of the line is going to be exactly the same when you're talking about the absolute value function. So let's talk about the absolute value function. But any negative x values here, instead of becoming negative y values, they just pop up and become positive y values. So this is actually what happens to the absolute value. Watch my magic. The sound effects really make it. Boom. Huh? How about that, ladies and germs? It's still like it's almost like a line. It still has a straight line quality to it, except now it's taking any negative x values and making them the positive versions of them. It's that annoyingly overly optimistic kid, you know, who would just find a silver lining and find something to be optimistic about during like nuclear war or something. It's like, okay, quit being so happy all the time. Sometimes you can, not be sad, but you can view a situation realistically. I'm rambling. So it creates the V shape. And now I'll go ahead and put the arrowheads here. It creates a V shape like that. That's really interesting. It still crosses through the origin because if I plug a 0 in, the absolute value of 0 is 0. In other words, an x value of 0 yields a y value of 0. That's not always true. Not every parent function is going to go through the origin. In fact, later on, when we get to chapter 4, we'll talk about exponential and logarithmic functions, and we'll see that those do not usually cross through the origin, the 0, 0 point. But yeah, so absolute value is V-shaped. And again, it just makes sense. It's not arbitrary. Let's talk about, yeah, I guess this is a good one to talk about. We'll talk about one more. This one's kind of optional. It's kind of funky. It's called the greatest integer function. And you see the word greatest, and it makes you think of something that's noble and magnanimous, something like that. The greatest integer function is kind of cool. Let me show you how it's written. This is probably something you haven't seen before, but the concept behind it isn't exactly ultra difficult. What you do is it has this weird brackets, and you know what? I'm just going to reconstruct it using the line tool. The less I draw by hand, the happier you will all be. It looks like a bracket, but then it has some extra business in it. And then it's going to close off that bracket over here. And then we're going to put an X in there. So it's the greatest integer function. Now, real quick, before we can talk about that, we have to just define an integer. You might know what it is. You might think you know what an integer is. An integer can be all the positive numbers that are whole. 1, 2, 3, 4. Of course, there's no limit to them. They keep going and going and going, or like Limp Bizkit said, they keep rolling, 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 rolling. But also in the integer set, we include 0. And then also in the integer set, we include all the negative versions of these positive whole numbers. -1, -2, and so on. So this is the set of integers. We will use a fancy Z. It's like a weird script Z we use to define this set. So the key point here is that an integer does not include anything that's halfway in between or partially. So 1.37 is not an integer. It's got to have no decimal expansion basically, or the first decimal place can just be 0 and nothing after that. So that's what it means to be an integer. And so maybe you knew that, maybe you didn't. The reason we use a z is because we use the German word for a number is Zahlen. Zahlen. So you learn something new every day. At any rate, what the greatest integer function is going to do is that if I plug an integer in for x, the greatest integer function, the function leaves it alone. Or rather, I should say it leaves it the same. So if I plug a 5 in, it leaves it as a 5. If I plug a -6 in, it leaves it as a -6. But things get interesting when you plug non-integers into it. If I plug a non-integer in for x, the function rounds it up, always up, not to the nearest, it rounds it up to the next integer. In other words, it's literally the greatest integer function. What is the greatest integer that is just above whatever you have, whatever you plug in? So real quick, let's do some function definitions. If your f of x is the greatest integer function, then f of 2, well, I plug a 2 in to the greatest integer function. And like I promised, it leaves numbers that are already integers, it leaves them alone. It doesn't try to round 2 up to the 3. But things get scary, not scary, they get interesting when I plug in non-integers. 1.5 is not an integer. It's going to round 1.5 up to 2, to the next greatest integer. But now 1.5 already, if we wanted to round it to the nearest whole number, 1.5 would have already rounded to 2. But what if we had 1.3? Normally you'd round that down to 1, but nope, the greatest integer function always rounds it up to the next value, always up. Negative numbers, it's not an absolute value, so it doesn't make them positive. Negative 9.7, now negative 9.7 is not itself an integer. And now you're thinking, does that round it up to negative 10? Well, no. Rounding up means you're going to become greater or larger than you were. So actually, the next largest integer is negative 9. If you think about it, because you're always going to the right on the number line whenever you're rounding up, which is a little confusing. But this is what happens. It sends it to the next largest integer. So, kind of an interesting concept here. What we're going to see is that the graph of this creates something called a step function. It's going to create something called a step function. So let's peer into the graph. Let's see, what will a graph look like? And let's investigate x values of 1 and x value of 2. What's going to happen here is that when you, and so we'll look at the y-axis real quick as well. What's going to happen to this is it's not just going to create a single line. No, no, no. When you plug an x value of 1 in, when you put a 1 into this, since 1's already an integer, it leaves it as 1. So that means this point is on here, 1 comma 1. But the second you go a hair greater than 1, say 1.02 or something, just a hair above it, all of a sudden it's going to snap it up and round it to 2. So here's what actually happens. It's going to come up, so if you put 1.01 in there, it's going to round it up to 2. If you put 1.5 in there, it's going to round it up to 2. If you put 1.999 in there, it's going to round it up to 2. So what happens is, if you put a 2 in there, it stays as 2. What happens is you get a flat line. You get a flat line for every x value between 1 and 2. And then what we have to do is we have to put something called a hole or an open circle here, saying that whenever x is exactly equal to 1, you use the solid circle, you use the filled in one, and you ignore it right here. And that just kind of gives you an idea of the boundary. And so what that does is that actually does something real funky. It's going to create another hole here. It's going to make for a step function. If you continue the pattern, here's the blue line again. Here's another hole. Here's a blue line again. And this step function is right continuous, we call it. But we don't have to worry about that. Here's another hole. It's going to keep this kind of pattern going down, and it's always going step down. And that's pretty cool if you ask me. Same thing going on here. Everything between 2 and 3, except for 2 itself, automatically rounds up to 3. So we keep the steps going. And of course, I can't draw them all, but just imagine the steps keep going, going, going. They keep going down, down, down. This is called a step function, because just look at its basic shape. Definitely, it is discontinuous at every integer, because when you look at the integer 1, from the left it's doing one thing, but you have to lift your pencil up here to draw what it's doing to the right. Now everything in between is smooth. I can draw a nice smooth line there. But at the integers themselves, I have to step up. Now, if you ever plan on studying statistics at some kind of level, now my master's degree was in statistics, so I'm a real statistics nerd, a real stat head. And I see step functions and I automatically think about certain types of probability functions, specifically discrete probability functions tend to be graphed as step functions. And I don't know why I do a nerdy voice. It's not that I think math is for nerds. It's just, I do nerd out over statistics just a little bit, maybe a little bit too much. I also nerd out over Star Wars. I also nerd out over Battlestar Galactica. So sue me, okay? But not literally. Please don't sue me. I don't want to be sued. It's not fun. So, greatest integer function, step function, you may come back to that someday. You may see it again. Finally, for this section, let's look at piecewise functions. These are functions that have different definitions based on the domain, or rather based on different parts of the domain. And I think it's better to just show you an example of this. Let's pick a new color. How about orange? What you're going to do is, instead of just writing the function and say, oh, it's -3 minus x, which is just the linear function negative x minus 3, which would then have a slope of -1 and a y-intercept of 0, -3. Instead, and let me move it, I need a little more space than that. Instead, a piecewise function defines the function differently for different parts of its domain. So what it does is the function is defined as -3 minus x for all x values less than or equal to 1. And then this, for this particular piecewise function, for all x values greater than 1, you use the negative 3 plus 2x part. Okay, so maybe you've seen a piecewise function before, maybe you haven't. But this means that if you wanted to find different values, if you wanted to find f of negative 2, well, negative 2 belongs on this part of the domain. Negative 2 is less than or equal to 1. So I'd plug it into the first piece. And it becomes negative 3 plus 2 becomes negative 1 itself. F of 1 then, I plug a 1 in for x. That still applies to the first piece here. That still applies because x less than or equal to 1. So negative 3 minus 1 will give you negative 4. But then as I try to plug in any any x values greater than 1, so how about 5? Now I jump over to the second piece here. And so it's going to be negative 3 plus 2 times 5. We won't spend too horribly much time. 2 times 5 is 10. 10 minus 3 becomes positive 7. So all a piecewise function does is it creates different graph or different looking graphs based on different parts of the domain. It changes the thing. Now in both cases, these were just lines. This had a slope of negative 1. This line had a slope of positive 2. So let's do this. Let's look at the graph. Let's look at the graph of this. So let me change my screen. Hey, there you go. Look at that. Ah, this is what's happening. Now, I had to define the piecewise function over here on the Desmos grapher. Now, normally I don't like just using graphing tools. I like us to think about these things clearly, but I think drawing this by hand in Zoom, maybe if I was on a whiteboard in person with you, but in Zoom, it's a little bit different. So what we can see is, here's the first part, negative 3 minus x for all x values less than or equal to 1. And so that creates a line with a y-intercept of 0, negative 3 and a slope of negative 1. But suddenly the line stops because at the x value of 1, and we can zoom in here, zoomify. When x is equal to 1, we come over here and suddenly we have to switch over to the new part. Now technically, and the Desmos grapher likes to omit this, we would leave the line solid here, but we'd put an open circle on this blue part because that open circle, when x is exactly equal to 1, it's hard to tell, should I be using the blue line or the red line? And neither of them seem to tell you right off. That's why we use an open circle. If I use an open circle on the blue line, it says, no, don't use the blue line. When x is equal to 1, use the red line because it doesn't have that open circle. That open circle is like saying, no, not this one. So imagine there's an open circle here at this point. And then when x is greater than 1, we get a line that has a y-intercept of negative 3 and a slope of positive 2. So it's now a positively sloped line. Now, of course, it's not actually going to get a chance, this part, to cross through its y-intercept because that would require an x value of 0 to get the y-intercept. And that's just not defined in this part's domain. So that's kind of cool, I think. Let's look at a different piecewise function. Let's look at another one, and I'm going to show you how you do it in the Desmos grapher. We want it to be for all x values. We want it to look like 5x. And we'll zoom out of this graph here as we need. So, and I just want less than There we go. That's what I wanted. Okay. So for all x values between -5 and including -5, but less than -1, I want it to be 5x, which is a positively sloped line. Then for all x values between -1 and 0, but not including 0, I want it to be the function -5, a constant function, which means it would create a horizontal line. And then finally, I want it less than or equal to 2. I want it to be a quadratic. Ooh. Now we can look at the graph of this piecewise function. So for all x values greater than or equal to -5, so here's -5 on the x value, but less than -1, it's this red line. It's this red line here. Notice that this thing is defined not for the entire real number line. Notice I didn't say for all x values less than -5 and all x values greater than 2. No. The real number line, it's only this piece right here. So this function is only defined for x values between -5 and +2. And then there's nothing outside of that. So the domain would just be -5 to 2. All x values between that. Excuse me. And so now this is what's happening. You get a positively sloped line for the first part, but then this middle part, remember, it's just, let me maybe space it out a little so you can see it. It's the line y equals -5, which is a flat line, a horizontal line. And so that's what it's doing. Between -1 and 0, it's this blue line. And then finally, for all x values between 0 and 2, +2, it becomes a quadratic. So it's only part of the parabola, though. It's missing the other part of the parabola because the domain is not defined there for that green part. So what we can see is this is a different piecewise function. It's nice that Desmos does colors, just different colors for the different pieces. I like that. What we can see, though, the most important thing is that this thing is actually still continuous. The last one was not continuous. There was a discontinuity there. There was a point where the graph jumped. But this one is nice and smooth. You got the red line and, ooh, look. You could, now you have to change the shape, but you could keep drawing. It doesn't jump off at any point. Keep drawing and, ooh, look at this. It goes seamlessly right into the green parabola here. So this thing is actually continuous. What we had previously was not continuous. So continuity rears its ugly head once more. Any questions on that? That's going to be it for section 2.6. Do you guys have any questions about 2.6? Take a good moment to pause. Questions, preguntas? Okay, so real quick, let me take attendance. Right quick, while it's on my mind. Mind on my money and my money on my mind. And then what we're going to do is we're going to bust out into the next section. Okay, so now we've talked about piecewise functions. Now we need to talk about what are called transformations of functions. So this will be section 2.7. It's called graphing techniques, but a better way to think about it is what we'll call transformations of functions. So transformations of functions, what we're going to be doing here, in the last section, we looked at a whole bunch of um, we looked at a whole bunch of different parent functions, the basic shapes they can make, all that jazz, all that business. And what we saw is that it wasn't always super interesting, unlike my Pokemon card collection, which is always interesting. So it wasn't very super interesting. So you just had like a boring parabola for the x squared function, and you're like, okay, what can I do to that thing? Because a lot of parabolas, when we actually graph them, a lot of them don't come out to be that pretty. You're right. So transformations of functions is going to kind of give us that. Now, if we were in class together and I was writing on a whiteboard with you, I would write out a lot of the things that I'm about to show you. But I think because we have the Zoom, but because I can screen share with you, I think it's better for this lesson today for me to point you at some other resources I have found that are going to help us. They're going to help us. So let's look at some of the different types of transformations. We can do reflections. So let's just start from the top with this one. So the first thing we can do, we can actually do a vertical translation. Vertical translation. And what a vertical translation does is it takes a parent function and it can shift it up or down. So check out the parent function x squared, the standard parabola. It's going to be represented by this gray dashed line here. That's the original parent function we started with. If I wanted to move it down 3 units, I would take x squared and I would subtract from the entire function a 3, say. So I take this and I shift every single point goes down 3 units. This point over here goes down 3 units. This point, 3 units. This point, 3 units. The origin point goes down 3 units. So subtracting something from the entire function has the effect of shifting it down, straight down, and then nothing else. And if you want to shift up, you need to add a number, add a positive number to that function. It kind of makes sense. You can look at these tables here. Yeah, you can look at these tables here. It's just saying that if I plug -2 in for x, -2 squared is 4, -3 gives me +1. Oh, okay. I plug a -1 in for x, I get a -2. I put a 0 in for x, I get a -3. So remember, you can always do a graph by getting just a whole bunch of points on the graph and hoping that when you graph those points, you can see the shape starting to form. Oh, look, here's those 5 points graphed, and okay, I kind of see a parabola shape forming. In general, that's kind of a dangerous graphing technique because it's better to understand the parent function, what the basic shape's going to look like, what the key points ought to be on that, and graph it that way. So yeah, a simple adding or subtracting of a number will shift it either down or up. Now again, this is kind of what the terminology is. If you want to do a vertical shift, and sometimes you also call that a translation. What you do is you starting with the parent function f of x, you add something to it, or you subtract something from it, subtract a value from it. This shifts it up b units. This shifts it down b units. But again, notice where the action's happening. You have the whole function and then you add something to the entire function. What we're going to see is that a horizontal shift or translation works a little differently. You take the function, but you actually do something to the x. You let the change happen on the ground floor with the x first. Then you apply the function outside of it. And then it also has a weird other effect that if I subtract from the x term and then apply the rest of the function outside of it, it's going to shift it to the right b units. To the right, but I subtracted something. Going to the right is like going the positive direction. Well, this is one of the most confusing parts of doing this graphing techniques section, is that whenever you apply something in the vertical sense or to the entire function outside of the function, it goes along in the usual direction. Oh, I'm adding, so it's going to go up. I'm subtracting, it's going to go down. But whenever I apply it to the x first and then plug that into the function and apply the function around it, it's got like this weird opposite effect. Technically, what's actually happening is that you're forcing the function to overcome an obstacle. So it's hard to describe why it has the opposite effect. But for the moment, we'll say that it does. And if you add a number in with the x, shifts it left b units. So it goes kind of the opposite direction when it's applying it with the x or with the horizontal. So that is going to be a little bit confusing. Also, what the heck does it mean I add b to the whole function, but down here I added in just with the x? Here's what I mean by that. If you had your function f of x was, say, x cubed, then if you add a 4 to it, what I mean is you take the original x cubed and then you add 4. And so that would take the x cubed parent function and shift it up 4 units. But when you use this type of definition, when you say bring the number in on the ground floor with x, it does something a little bit different. I need more white space. So sorry, let me rewrite that. So yeah, let's say you had x cubed. If I do something to the entire function, I do it there. So this will create a vertical shift upwards. But if you want a horizontal shift, and you still have a parent function of x cubed, if I do it inside with the x, what that means is I'm going to do it to the x first. Then I'm going to apply the function, which is to cube it. I'm going to apply that out after I've taken care of it with the x. Notice the difference. Here, the x cubed happens first, then I add the 4. That's going to do things to our y values or or cause vertical shifts. But I brought the 4 in with the x first, then I did the cubing. That's what this notation means. That's going to have effects or impacts in the horizontal direction that go along the x-axis. So what this does, this shifted the function upwards or up 4 units, not ubnits. But what this did was it happened with the x on the ground floor. It's going to cause a horizontal shift. And then we have to remember that little chart that said, well, if I'm adding, it's actually going to go to the left. It's going to do the opposite of what we expect. So this shifted the function left 4 units. So that is a little bit funky. That's a little bit weird. But let's go back to that little website I found. So that's how you get a vertical shift. So if you wanted to sketch the graph of the square root of x plus 4, take your basic square root function here, which is drawn much better than I drew it. People often ask me, Josh, where did you pick up your art skills? You have such amazing art skills. And I say, well, they basically haven't improved since I was in kindergarten. And I give a smug smile. Uh, so you interpret that however you want. So if we took the parent function square to x, but we added 4, and notice that adding a 4 is happening on the outside of the square root. That tells me it's a vertical move. If I had extended this square root to cover the 4, different story. Now you're shifting this to the left 4 units. So it's a subtle difference, but it's an important one to pay attention to. So that's what's going on. So now a horizontal translation, a horizontal shift, notice that suddenly whatever you're trying to shift by is getting in on the ground floor with x. And suddenly, if I have my original parent function x squared, just making the nice parabola here in the gray dashed line, if I add 3 to the inside with the x, then apply the squaring, the quadratic, or excuse me, I guess quadratic nature of the function to it after that, it's going to shift every single point to the left 3 units. So this point comes to the left 3 units. This point comes to the left 3 units. And it's probably important to remember that a graph is nothing more than all the xy coordinate pairs, all the points that exist for this function. And then you just kind of draw it smoothly. So really, a graph is nothing more than, an infinite, almost infinite, or seemingly infinite number of points, all just kind of drawn together, and you connect the dots, so to speak. So then if I wanted to subtract 3 units first from the inside, it's going to have the opposite effect that you would expect. You expect it to go left, because going to the left is going in the negative direction. But that's not quite how it works. We got to kind of opposite it in our minds. And yes, I just used the word opposite as a verb. So subtract 3, so actually it's going to go right 3 units. Every single point shifts to the right 3 units, and so on and so forth. Let's pause for a moment. Do you guys have any questions on that? Any questions? Is it making sense?
Yeah.
Cool. Thank you very much. I appreciate it. So far it's making sense. It's good to go. Horizontal shifts. So again, the graph of x cubed is shifted to the right 4 units here. That's because I actually subtracted 4 first from the x, then applied the cubing. Ah, the absolute value function. Oh, suddenly they're getting next level with it. So they first, with this, remember the absolute value function created the v. It created a v function, v shape. Here what they're doing is they're adding 3 in with the x. So that's going to shift it to the left 3 units. Then they're subtracting 5 outside the absolute value. So they're actually also shifting it down 3 units. So both of those things are happening. So they're giving you a 2 for 1. So start with the basic v function here, the basic absolute value, this one. We're going to shift it left 3 units, and then down 5 units. You could just think about it. I know it's got to be the v function. I'm not changing the shape of it. So I'm just shifting this bottom point left 3, down 5, and then I can create the v again after it. So generally speaking, doing horizontal and vertical shifts, translations, is perhaps the more easier. It's the more easier possibility here, the most easiest of the types of transformations we can do. We didn't talk about the base rational function, but if we did, that's what would happen. Next up, and I'm sure your yearbook has, or some yearbook out there is called Reflections, but it has nothing to do with yearbooks or anything like that. Mr. Gunther is really weird. Well, that hurts my feelings a little bit. No, it doesn't. Anyways, so reflections. Reflections is exactly what it sounds like. You're generally speaking, you're going to be reflecting about the x-axis or the y-axis. And again, which axis you're going to be reflecting around depends entirely on where you apply the reflection. Do you apply it first to the x? and then apply the function around it? Or do you first do the function and then apply the reflection after the fact? That is an important distinction. It's easy to get that confused. So imagine our parent function is the square root of x, the basic square root of x, which remember looks like this. So here's where things get a little bit wonky. If you apply the negation, so basically the way you're going to be reflecting is you're going to be multiplying by -1 somewhere. That causes a reflection. If you apply that negation first to the x on the inside, then apply the function around it. Now you're probably thinking, Josh, but I can't take the square root of negative numbers in a graph. Except, imagine x was already a negative number to start with. Imagine x was -3 to start with, which normally I couldn't take the square root of -3, but then I apply the negation to it, and now it becomes the +3 before I take the square root. So some funny business is happening here. Now, if I were to apply this reflection, only negative x values are allowed so that they then get negated and become positive before I take the square root. It's a really wonky idea. So if this here is the parent function, the basic function for a square root, then if I negate on the inside, I hit the x first, it's going to reflect it about the y-axis. It's going to go, woo, make a little like a mirror down the middle here, and it reflects it about the y-axis. And now suddenly, just looking at the blue part, suddenly only negative x values are allowed, like we discussed, and 0 is allowed. And so this part is completely gone when you're looking at the reflection. That one will kind of keep you up at night when you think about it. Kind of like, I don't know if you're watching The Matrix and he goes and he visits the Oracle and she says, what if I never told you you bumped your head? Would you have bumped your eye? Anyways, not to digress. So a reflection about the y-axis requires you to get in on the ground floor with the x. And the reason is that it now requires you to flip around, to flip all your x values to the other side, which is exactly what it means to be a reflection about the y-axis. So what was once +2, you now have to have the same y value pop out of that for a -2. And if you want to reflect about the x-axis, you apply the negation, in this case, outside the square root. You do it outside of the function. So we'll look at that in more detail next time. We're almost out of time. So we got about halfway through 2.7 as well. So we had a good productive day in class. I think we did all right today. Does everyone else think we did all right? Yeah, I hope so. You guys feeling good? You guys feeling comfortable and confident? Maybe, hopefully. I think a lot of you did really well with the material last time about linear functions. A lot of you expressed to me that that was something you were pretty comfortable with, which is good. So y'all have a great weekend. As I buy the last couple seconds here, y'all have a great weekend. Oh, there it is. Thank you so much. We'll see you guys on Tuesday once again.